Hello everyone. Today we want to talk about 12.1 parametric equations, the second part. In this lecture, we will talk about how to find the slope of the tangent line of a parametric curve. And we will also talk about how to find the arc length of a parametric curve. So first, let's take a look at this box, the derivative for parametric curves. With that x equals h of t and y equals k of t, where h and k are differentiable functions on this interval. Then the slope of the line tangent to the curve at a point corresponding to t is given by this equation. So, excuse me. So notice that the slope is always rise over run, where the rise means the change in y and the run means change in x. Okay, so that's why we always have dy over dx, the change in y over the change in x. Okay, now notice that if possible, you can eliminate the parameter to get an equation in x and y only. Okay, and then you can find dy over dx by taking the derivative of y with respect to x. However, we mentioned previously, sometimes it's not possible to eliminate the parameter. Okay, so in that case, how do we find dy over dx? So right here, the idea is to treat dy over dx as a fraction. Okay, for example, if you have 12 over 4, okay, 12 over 4. Okay, and then we can divide both top and the bottom by a non-zero number. For example, right here, I can divide both top and the bottom by 2 to get 6 over 2. Okay, 12 over 4 is the same as 6 over 2. Okay, so we can divide both top and the bottom by the same thing. So right here, I will need to divide both top and the bottom by dt. Okay, so you can see that right here we have dy over dt as my numerator, dx over dt as my denominator. But notice that dy over dt is the derivative of y with respect to t, and since y is a function of t, that means dy over dt is k prime of t. Right? Y is a function of t. So this means the derivative of y with respect to t. So you take the derivative directly. Similarly, dx over dt is the derivative of x with respect to t. And since x is a function of t, we just take the derivative directly. Okay, so right here, dy over dx is k prime of t over h prime of t. And of course, right here, we don't want h prime of t to be 0. Okay, so provided that h prime of t is non-zero. It's okay? So notice that the idea is to divide both top and bottom by the same number, non-zero number. Okay, like 12 over 2, 4 over 2. Okay, and notice that the slope, okay, it doesn't matter which equations you are using. It doesn't matter if you're using the equations in x and y or if you're using parametric equations. The slope is always rise over run. Okay, let's take a look at example 1. Consider the curve defined parametrically by x equals t plus sine t, y equals t minus cosine t. Okay, right here, t is between 0 and 2 pi. So the first part, we want to find a Cartesian equation. Okay, so notice that a Cartesian equation means equations in x and y. Equation in x and y. Okay, I want to find a Cartesian equation of the tangent, okay, of the tangent lines, okay, to the curve at a given point when t equals pi over 4. Okay, when t equals pi over 4. Now notice that if we want to find an equation of a line, okay, we need two things. We need a slope, we need a point, right? So we can use the point slope form. Okay, to find a slope, okay, notice that the slope of the tangent line is dy over dx. So that means we will need to find dy over dx. Okay, but right here we don't have y equals a function of x. Instead, we have parametric equations. Okay, so right here we wanted to find dy over dt and dx over dt respectively. So right here, dy over dt is the derivative of y with respect to t. So that should be 1. Okay, the derivative of t is 1. The derivative of cosine is negative sine. So we have plus sine t. And dx over dt is the derivative of x with respect to t. So that means we have 1 plus cosine t. Okay, so thus dy over dx. So notice that the slope of the tangent line, okay, the slope is always dy over dx. Okay, rise over run. And right here, dy over dx is dy over dt over dx over dt. So that means I wanted to put 1 plus sine t in my numerator and 1 plus cosine t in my denominator. Okay, so that's your slope. Now notice that this slope, okay, you can see that this slope right here depends on the value of t. When t changes, the slope will change. Okay, we want to find a specific slope at t equals pi over 4. Okay, so right here, our slope m is the derivative of y with respect to x evaluated at t equals pi over 4. Okay, so that means right here I will have 1 plus sine pi over 4 over 1 plus cosine pi over 4. Is okay? Now notice that sine pi over 4 is square root 2 over 2. Cosine pi over 4 is also square root 2 over 2. Okay, so you can see that the slope right here is 1. Okay, the slope is 1 when t equals pi over 4. Okay, so previously we said that if you want to find an equation of a line, you need two things. You need a slope, you need a point. Okay, right now we have the slope. We want to find a point. Okay, so notice that the point refers to the coordinate of that point, right? So you need x value and a y value. Okay, so right here, to find the x and the y coordinates, you will simply put t equals pi over 4 into these equations. Okay, so when t equals pi over 4, my x value is pi over 4 plus sine pi over 4. Okay, and this is just pi over 4 plus square root 2 over 2. Okay, and my y is t minus cosine t. So t minus cosine t. So that should be pi over 4 minus square root 2 over 2. Is okay? Okay, let's finish this. Therefore, okay, the Cartesian equation of the tangent line to this curve at t equals pi over 4 is, okay, we use the point slope form. So y minus y value, right? Y minus y value equals slope times x minus x value. It's okay? This is y minus, this is the y value. See here, pi over 4 minus square root 2 over 2. Okay, y minus y value equals slope times x minus x value. Okay, so the general form should be y minus y0 equals slope times x minus x0. Okay, so that's the general form for point slope formula. Point slope form for the equation of a line. It's okay? Now, of course, you can leave your answer in this form. If you want to simplify, that's good. Okay, you just need to be careful about the math. Okay, right here you will need to distribute this negative sign. Okay, similarly, you will need to distribute this negative sign. You should have y equals x minus root 2. Okay, again, if you want to simplify, that's your answer. If you don't want to simplify, that's good. Okay, unless the problem asks you to write a specific form. For example, this is the slope-intercept form. Okay. Okay, let's make a quick review. Notice that the slope, no matter what equations you're using, okay, the slope is always right over run. It's always dy over dx. Okay, the way we find dy over dx by using parametric equations is to find dy over dt and dx over dt respectively. And then I divide dy over dt by dx over dt. It's okay? Next, let's take a look at page 2. Now we know how to find the slope. Okay, so let me write down the slope right here. So dy over dx is basically dy over dt over dx over dt. Okay, so right here, we want to find when the curve has a horizontal tangent line. Okay, so notice that horizontal tangent line, it means the slope is 0. Okay, that means the slope equals 0. So right here, that means this quantity, dy over dt over dx over dt, should be 0. Okay, that means your numerator, dy over dt, should be 0. Okay, but your dx over dt is not 0. Okay, for example, if you have 0 over 3, that is 0. If you have 0 over 5, that is also 0. It's okay? So numerator equals 0, dy over dt equals 0, but the denominator cannot be 0. Okay? Now, we also want to find out when the curve has a vertical tangent. So notice that for a vertical line, the slope does not exist. Okay, the slope does not exist. Okay, so that means right here, you want your dy over dt to be non-zero, but you want dx over dt to be 0. Okay, so basically if you divide 3 by 0, we know that does not exist, right? So if you have 3 right here, 0 right here, that's not valid. So that means the slope does not exist. Therefore, we will have a vertical tangent line. It's okay? Now you might be wondering, what if both your numerator and the denominator are 0? That is a very good question. Okay, so notice that in the past, we learned, okay, somewhere in calculus 1 and calculus 2, okay, somewhere right there on the textbook, we learned a form called 0 over 0, right? We call it an indeterminate form. And we say that if you have indeterminate form, you want to use low beta 0. Okay, so right here, if dy over dt equals 0 and dx over dt equals 0, then we should consider low beta 0. Okay, of course, to use low beta 0, we will need to take the limit. Okay, so we will take the limit and then apply low beta 0. It's okay? That is the worst scenario. Okay, if both dy over dt and dx over dt are 0. Okay. Let's take a look at example 2. Consider the curve defined parametrically by x equals t plus sine t, y equals t minus cosine t. Okay, I believe this is the same pair right here. Yeah, x equals t plus sine t, y equals t minus cosine t. Okay, so we can just use what we had previously, okay, to work on part B and part C. Okay, part B, we want to find all points on the curve where the tangent line is horizontal. And C, we want to find all points on the curve where the tangent line is vertical. Okay, so by using A, we have dy over dt. Well, even if you don't use A, you still can take the derivative directly. Okay, it's not too difficult. Okay, so dy over dt is 1 plus sine t. Dx over dt is 1 plus cosine t. Okay, so right here, we will set dy over dt equals 0. Okay, because I want to know when my numerator, okay, so recall that dy over dx is dy over dt over dx over dt. Okay, so I want my numerator to be 0. Okay, so I set my numerator to be 0. So that means 1 plus sine t equals 0. So sine t equals -1. Okay, and then how do we find sine t? We have sine of t equals -1. How do we find t? Now notice that this is a trig function, right? So that means you should have infinitely many solutions. Okay, t equals 3 pi over 2. Okay, you might notice that t equals 3 pi over 2 is one of them. Okay, but notice that if you add 2 pi, sine of 3 pi over 2 plus 2 pi is also -1. Okay, if you minus 2 pi, you still get -1. Okay, because sine is a periodic function. Remember, we have infinitely many solutions. Okay, but right here we have the domain. Okay, we only want t to be between 0 and 2 pi, so that means 3 pi over 2 is good. It's okay? Okay, I need to mention this because what if the problem says t is between 0 and 4 pi? Right? So you will have two answers. Okay, there will be two t's. It's okay? So always take a look at your domain. Okay, and remember this is a trig equation. Okay, so you should have infinitely many solutions right here. Okay? And then we wanted to set dx over dt to be 0. Okay, because I want to see when my denominator equals 0 and I will exclude those points, right? Okay, so that means 1 plus cosine t equals 0. So cosine t equals -1. In theory, you should have infinitely many solutions. Okay, but notice that t is between 0 and 2 pi. That means we only have one, t equals pi. Okay, now fortunately, these two numbers are different. Right, these two numbers are different. That means it is impossible for dy over dt and dx over dt equal to 0 at the same time. Okay, so that means we're good. We don't have to worry about L'Hopital's rule. Okay, so let's finish this question. So for B, when t equals 3 pi over 2, okay, when t equals 3 pi over 2, I know my dy over dt, my numerator is 0, but my denominator is not 0. Right? Because the denominator equals 0 only when t equals pi. So that means when t equals 3 pi over 2, my denominator cannot be 0. Okay, so that means the curve has a horizontal tangent line at t equals 3 pi over 2. Okay, but notice that the problem asks us to find a point. Okay, so we need to give the coordinates of this point. So that means we will give an order pair. Okay, so right here you will need to find the x value and the y value. Okay, so notice that, let me copy x right here. Y is t minus cosine t. Okay, so right here, when t equals 3 pi over 2, I will plug in this for t. So I have my x value as 3 pi over 2 plus sine of 3 pi over 2. But sine of 3 pi over 2 is -1, so I have 3 pi over 2 minus 1. Okay, and then I will need to do the same thing for my y value, 3 pi over 2 right here. Okay, and when I plug into this function, cosine 3 pi over 2 is 0, so minus 0. Okay, so that's our point. So notice that this is the x value, this is the y value. Okay, we need to find an order pair, okay, x and y. Okay, let's finish this. So vertical tangent. Okay, vertical tangent happens when your denominator equals 0, but your numerator cannot be 0. Okay, so when t equals pi, our dx over dt, this is x, okay, dx over dt is 0, but dy over dt is not 0. Okay, so that means the curve has a vertical tangent line at t equals pi, okay, but we also want to find the x value and the y value. So let me plug in pi right here. Plus sine pi is 0. Okay, so we have pi. And right here, let's plug in pi. Pi minus cosine pi. Okay, cosine pi is -1, so I have a +1. It's okay? Does that make sense? Okay, so notice that the slope, if the tangent line is horizontal, that means the slope equals 0. Okay, the slope equals 0. So that means dy over dt, your numerator has to be 0, but the denominator cannot be 0. Now, if the tangent line is vertical, that means the slope does not exist. That means your numerator is not 0, but your denominator is 0. Okay, this is x. Okay, next we want to talk about how to find the arc length of a parametric curve. So let's take a look at page 3. So notice that previously we introduced the arc length formula, right? We say that there are two, okay, but they all come from the same idea, the Pythagorean theorem. Okay, if you forget, make sure you go back and review. I believe it's 6.5, I think. Yes, 6.5. Okay, 6.5. Okay, so previously we have ds. Okay, we say that this first part right here comes from the Pythagorean theorem, right? ds equals the square root of dx squared plus dy squared. Okay, and we say that by using some simple algebra, we can create different formulas. So right here, basically what you did is to factor dx squared out. Right, you factor dx squared out of the square root, out from the square root. Right? So you see here, if I factor out dx squared from the square root, I have a dx outside, but this becomes 1, this becomes dy over dx quantity squared. Right? And we say that right here, I don't need to factor out dx squared. Instead, I can factor out dy squared. Is okay? So see here, if I factor out dy squared out of the square root, then I will have a dy outside, right? This becomes dx over dy quantity squared, and we have +1. Okay? Now you can see that right here, you will be able to integrate with respect to x, and right here you will be able to integrate with respect to y. Is okay? Now for parametric equations, okay, of course, you're welcome to use these two formulas. Okay, once you find dy over dx or dx over dy, you can use these formulas. Okay, but sometimes it will be really messy because you can see that right here, dy over dx for this particular problem, dy over dx is 1 plus sine t over 1 plus cosine t. Wow, that's really complicated, right? Okay, so usually we don't use these two formulas. Instead, we will create a new formula for arc length. Okay, again, it's not really new. Okay, we still use the same idea. Okay, this formula still comes from the Pythagorean theorem. Okay, but we will make it look different. Okay, so it will be in a different form. Okay, so notice that right here, I can factor dx squared out of the square root, so I can integrate with respect to x. Right here, I can factor out dy squared out of the square root, so I can integrate with respect to y. So if I want to integrate with respect to t, I need to factor dt out of the square root. Okay, so right here, factor dt squared out from the square root. Okay, so that means right here, you will have square root of dx over dt quantity square plus dy over dt quantity square. Okay, and then you have a dt outside. Okay, and you want to integrate from some. So notice that here t is from a to b. It's okay. So take a look at these three different forms. Okay, they are totally different. Okay, they are totally different, but they all come from this expression. They all come from the Pythagorean theorem. Okay, so that's why I wanted to show you how we get these formulas. Okay, I'm not just telling you, hey, use this formula, use this formula, use this formula. Okay, because if you treat them like separate or different formulas, okay, there will be three different things you need to memorize. Okay, but if you integrate, I mean, if you put them side by side and understand how to obtain these formulas, okay, integrate this idea. Okay, I'm not saying integrate this quantity, integrate this idea, then you should be able to memorize this because they all come from the same quantity here, the same expression. Okay, the difference is that I can factor dx squared out, I can factor dy squared out, I can factor dt squared out. Okay, it really depends on whether you want to integrate with respect to x, with respect to y, or with respect to t. It's okay? Let's take a look at example 3. Consider the curve defined parametrically by x equals e to the tth power, y equals t times e to the negative t. Okay, right here t is between e and e squared. Now we want to set up, but do not simplify or evaluate an integral that represents the arc length, well, the length of the curve on the interval, the arc length. Okay, so right here, remember, we want to use this quantity, okay, and this is from the Pythagorean theorem. Okay, so I want you to find dx over dt, which is e to the t. I will also need to find dy over dt. Okay, so notice that right here, y is t times e to the negative t. So that means when you take the derivative, you need to apply the product rule. Okay, so just in case you forget, if you want to take the derivative of f times g, that's f prime g plus f g prime. Okay, that's the product rule. Okay, so right here we have 1 times e to the negative t plus t times e to the negative t times negative 1. Okay, so I should have e to the negative t minus t times e to the negative t. It's okay? So the problem only asks us to set up. Okay, so your arc length formula should be the integral of the square root dx over dt squared. Okay, this guy, I don't care what it is, I just need to square it, right? And then plus dy over dt squared. The same, I don't care what it is, I just need to copy it. So e to the negative t minus t times e to the negative t 20 squared. Okay, and I will integrate with respect to t from e to e squared. From e to e squared. It's okay? Okay, any questions? Well, if you have any questions, please do not hesitate to email me, okay? Uh, so let's make a quick review. In this lecture, we talk about two important things. First, we want to find the slope of a parametric curve, okay? And second, we want to find the arc length of a parametric curve, okay? So for the first part, define the slope, and remember the slope is always defined to be rise over run. That is the change in y over the change in x. So it is always dy over dx. Okay, it is always dy over dx. And to find dy over dx, okay, you simply divide both top and the bottom by the same dt. Okay, so you have dy over dt on top and dx over dt at the bottom. Okay, so that's the slope. Okay, and we also talk about how to find horizontal tangent lines and vertical tangent lines. Okay, basically horizontal means slope equals 0. Vertical means slope doesn't exist. Okay, so take a look at this portion. And the worst scenario is that when your numerator and your denominator are both 0. Okay, so you will have 0 over 0, and we called it an indeterminate form. Okay, so you will need to use slope beta 0. Okay, and finally we talk about the arc length, and we say that there are 3 different forms. Okay, so these two forms occurred in 6.5, and this form occurred in 12.1. Okay, it seems like they are irrelevant, okay, but they all come from the same Pythagorean theorem. Okay, they all come from the same expression. Okay, so if you can understand this, that will benefit you a lot. Okay, please make sure you practice the problems on Canvas. If you have any questions, please do not hesitate to let me know. Okay, thank you.